So I just wanted to get into our discussion of energy and momentum. We did two things yesterday. We covered conservation laws, and we also covered, conservation of momentum and of energy. And we also took a second look at the work energy theorem and the impulse momentum theorem. So a lot to cover, and I just want to outline what it is that we did. So we started our day looking at a few ideas. We looked at some energy demos where we ran sprint cars, we popped poppers, we used hand crank flashlights. My favorite though was when we went outside into the pavilion and we ended up grabbing the Alka-Seltzer tablets, putting them into film canisters, and letting them launch into the air. I've never done that one outside before. That's probably not a good thing to advertise, but it was pretty awesome how we got it to go up to the third floor of Stewart Hall from the pavilion, courtyard, whatever you want to call it. We kept it popping. Woo. Okay. Now, the thing that we were able to do, though, was name various forms of energy. Even if we didn't have a clear idea of what energy actually is, we were able to name some forms of it and kind of use our intuitive grammar school knowledge to come up with a picture of what energy is and what it does. Kind of touchy-feely, and then we tightened up that definition as we continued. So, we named what we suspected were various forms of energy: spring energy, gravitational energy, electrical energy, chemical, etc. One term we neglected was the term potential energy. And I know where we're going with that. I prefer not to use that term. I actually like to use the names gravitational energy and also elastic energy. And I'll use the term elastic potential energy just to make people happy. But the truth is, potential energy, I know what we're getting at. It's an older idea that potential energy is the capacity to do work. Okay? But then, people will say that all forms of energy are the capacity to do work. And I think I'd rather work with the notion of conservation of energy as our starting point and work backwards from there to discuss what work is in our class. So I'm not going to use the term potential energy. I'm going to use the term gravitational energy, elastic. Sometimes I'll call that gravitational potential energy or elastic potential energy. So to that end, we played with the demos, and then we were actually able to define what energy is in physics. And the surprising thing is energy is simply a bookkeeping system. And here's what we do. You get a system. You add up all its different ways of storing energy. A lot of those come from the demos that we did. And then we let the system do something. And then we go ahead and recalculate the energy at the end of the system doing whatever it's going to do. And although the energy may change form and hide in different places, when we account for all the little different hidey holes that energy has, and we add it up, the energy that we have at the beginning will be the energy that we have at the end of the process. And we actually have a name for this rule. It's called the conservation of energy. Now that sounds all nice and good. However, it sounds quite a bit abstract. And so what we did is we actually took this kind of big picture of what energy is, and we transformed it into a very powerful technique for approaching physics problems where we want to find dynamic quantities such as acceleration, force, speed, position, height, time, etc. And instead of writing down lots of equations, we can add up the energy before and after and use this to kind of tease out unknown quantities. In this class so far to date, we've dealt with 4 forms of energy. And they're essentially gravitational, kinetic, elastic, and dissipated. One small thing with the elastic energy, we did need to kind of talk a little bit about where that comes from. So elastic energy is when you have a spring, okay, and perhaps you compress it or you stretch it. Oh, the wonder of computer technology. So there's a spring. So we have 2 components to elastic energy. One is that when you've got a spring, it has a certain resistance to being stretched inherent in its makeup called the spring constant. This is the variable for it. What it tells you in real life is the resistance of the spring to being stretched. If K is small, we're talking about something like a slinky, very easy to stretch. If K is large, okay, we're talking about something a lot harder to move, like, say, a box spring. Okay, so big K, hard to stretch, low K, small k, easy to stretch or compress. And the next part of elastic energy is how much you stretch or compress the spring. Of the spring. Okay, that is terrible writing. So X is the stretch or the compression of the spring, okay, measured in meters. Now, we talked about a fourth form of energy called dissipated energy. That's the energy lost to heat, friction, etc. It exists. We just can't get to it. So here we go. Now, if you recall what we said with energy, look at a system, add up all the forms of energy, let it do what it's going to do, add up the energy at the end, and the number will be the same. And this seems like a very abstract idea, but it turns out we can turn this into real tools to solve problems. The first tool that we did, that we used, created, set up, whatever word you want to use, is the energy bar graph. What we did is this: we created some columns representing all the forms of energy that we see in a system so far. Okay. There we go. Very subtle of me. And then we have the energy at the beginning and the energy at the end. One small thing: you can't have dissipated energy at the beginning because friction hasn't done anything to the system yet. So you add up all the energy, you draw bars to represent the energy at the beginning and at the end of a process. You set them equal, and then you solve problems, which is what I'm going to do on the homework, really, but I want to make one small point. When do these types of energy occur? Just to be clear, you get gravitational energy when your height's bigger than 0, you get kinetic energy when you're moving, and you get elastic energy whenever you have a spring. One other thing I want to say is this usually becomes 0 when the spring has sprung. Okay, very little we can do with it after that. So again, I'm going to restrict my problem-solving examples to the homework, and I'm going to move on to the notion of work. So we said, okay, you've got energy at the beginning, and you've got energy at the end. We want to talk about the process of transforming from one form of energy to another, and work is the process by which, I'm going to say it this way, forces convert the means by which, write a little bit neater, the means by which forces convert energy from one form to another. A book will tell you work is force times distance. That's the formula. It's a good definition, mathematically speaking, but what work actually represents is the process by which forces act through a distance to convert energy. One small thing: if you show these notes and this video to any engineers in your family, so if your sister, mom, aunt, uncle, whatever, if they are engineers, they're going to look at what I'm telling you here, and they are going to tell you, look, technically this is displacement. And they're right, and I should say displacement, but here's the thing. I don't want to mess with the vocabulary, given how little time we have in the class and how much we do have to cover. So I'll just tell you right now, for us, for work, for our first physics class, we're going to use the term distance and displacement interchangeably because they're going to actually be interchangeable in the way that we set up problems. A very important point that we touch on, though, is this principle called the work kinetic energy theorem. And it simply says the work done on a system is the change in its kinetic energy from the final amount that you get minus the initial amount that you get. And it's all laid out there. We did want to contrast this idea with the impulse momentum theorem we did a couple of days ago, where this is another form of Newton's second law, but it has to do with collisions, crashes, etc. It's the collisions, crashes, etc., the catastrophic events version of Newton's second law, which you probably may not recall off the top of your head, but that's the one that says force makes an object accelerate. Rather than looking at the acceleration of the forces, we kind of smear out the time and the force together and just look at the change in momentum. So we've finished up the presentation part of, my goodness, Tuesday. This is just yesterday. I can't believe it. It feels like it was Monday. Looking at the conservation of momentum theorem. And the idea here is that if you have object 1 and object 2 and they crash into each other, okay, so you have a force on 2 due to 1 pointing this way, and a force on 1 due to 2, so they are equal and opposite forces. That's the third law. And you take the notion of impulse is the change in momentum. You take these two ideas and stick them together for crashing objects, and then one will fly off this way and two will go off that way. If you take this idea of crashing objects and combine them mathematically, which I will not do, we get a way of examining incoming and outcoming speeds and velocities, really velocities, by looking only at the collective momenta of the system. We call this principle the conservation of momentum, and we'll really see the practical application of it when we get to problems. So just to be clear, we have a lot of formulas today. Conservation of energy, work, kinetic energy, impulse, change in momentum, and conservation of momentum. The point is that what we're going to really be doing is examining how to use these in problems. And one small thing I want to say, I always hear students say, hey, Mr. Abdullah, how did you know how to use the formula that you used when you were solving this problem? Well, I have to say, I don't think in terms of formula. Here's what I do. All those discussions we have about what does energy mean, what is momentum in real life, what are forces, that physics is what I look at when I look at a problem. And then when I think about the physics that's going on using my definitions and my vocabulary and all the terms that I learned in lab, I take those ideas and they lead me to the correct formula. So it's not a question of just picking a formula because I'm smart. It's a question of examining the physics discussed in class and letting that guide me to the formula that I want to use. So that's exactly what we're going to do when we take a look at the homework.